All right, I'm going to give you some notes here about finding mathematical models that we can use for EK and EG. That's our goal in these notes here. So what about EK? Well, when something in general is, when work is done on something, we know that work is equal to change in energy. And we know that the thing that does work, or the things that do work, are forces. So work is equal to a force times a distance. If we have a constant force, then this area here is force times distance. It's just a rectangle equals work, which is equal to change in energy. Okay, so let's say we have something that's changing its kinetic energy. Maybe it's going faster, maybe it's going slower, whatever, but there's a force acting on it, so its kinetic energy is changing because it's getting faster or slower. So that is equal to force times distance. And we know that force is equal to mass times acceleration. So I can make that substitution here. And we also know that if we have constant acceleration, which is the kind of situation we're interested in, that one of our kinematics equations is this one. And this delta x here and the distance that something moves through, delta x is displacement, distance here, so I'm calling it distance here, I'm calling it delta x here, but that's the same thing, so that could just be d, right? And I'm going to do a little bit of rearranging of this equation here. I'm going to subtract the vi over to this side, and then I'm going to divide both sides by 2. So just a little algebra there. So that's equal to AD, right? I subtracted that over, and then I divided by that 2. And then I'm going to make, since that's A times D, and I've got A times D right here. Oh, hold on one sec. My pen ran out of juice. I'm just going to plug it in for 1 sec here. Well, not 1 sec, more like 10 secs. So bear with me for just a minute. That should be good for a little bit. So EK is equal to mass times, and then in place of AD, I'm going to put this expression here. Now, VF squared minus VI squared over 2. And then I'm going to do a little algebra to that and write it. So the 2, I'm going to make that a 1/2. And then I'm going to distribute the m, so it will look like this. You can stare at that for a second. Just convince yourself that that algebra is legit. Well, if change in kinetic energy is equal to this, that means that EK, this is final minus initial, so that means EK must be equal to 1/2 mv squared. So that is our mathematical model for kinetic energy. EK is equal to 1/2 mass times velocity squared. And notice that since the velocity is being squared, this is always positive. What about with gravity? Well, if we're interested in the work done by gravity, which is equal to change in energy, then if I've got this force, if this force is a gravitational force, then maybe it would make more sense here. Gravity acts in an up-down direction, so maybe we should, instead of calling that D, we could call that H, like the height something is at. So it's changing height here, and then the change in its gravitational potential energy would be equal to the area of this, and since the force of gravity is constant, that's just force of gravity times, and we're not going to call it distance here, we're going to call it height, because that's what matters for gravity, the up-down direction. So change in, and that would be like the change in its height there, change in gravitational potential energy is equal to the force of gravity is 10 times mass, that's how we've been finding that all along, times change in height. So if change in gravitational potential energy is equal to 10 times mass times change in height, that means that gravitational potential energy must be equal to 10 times mass times h. And what h, like height above what? So we're just going to choose the zero height to be whatever the low point is in our situation, right? When something's falling, then we'll take the lowest point to be the zero height. So I'm just gonna make it as easy as we can. Okay, so quick summary of what we did here. EK is equal to 1/2 mv squared. EG is equal to 10 times mass times h, and then we already knew that EK is equal to 1/2 k x squared, where k is a spring constant and x is how much you've either stretched or compressed the spring. I'm putting that in parentheses here. I'm just adding it in here because these are our three important mathematical models for energy. So, two quick examples for you here. What if you had a ball that you dropped, excuse me, so that's initial velocity is 0, and then it gets to the ground just before it hits the ground. It's cruising there toward the ground, and its height is now 0. And let's say its height here is something that's not 0. Let's just say its height is equal to h. Then can we find how fast it's going using energy considerations? So the first thing we would do is just make a quick LOL diagram here with the ball and the entire Earth in the system. And here at the beginning, in like position A here, it doesn't have any velocity, so it doesn't have any kinetic energy. This would be 0. This would be 0. But it's got some gravitational potential energy. Maybe like 4 little bars worth. And when it gets to the ground at situation or position B, now its height is 0, so it doesn't have any EG anymore, but it's moving toward the ground, so it has EK. And then our equation would very simply be EG equals EK. Right? Whatever we got here must be equal to whatever we've got here. And now I can actually do some math, or at least do some algebra here. I can say EG is equal to 10 mh, and EK is equal to 1/2 mv squared. So if I want to find how fast it's going at the ground, I just have to do a little bit of algebra. The mass cancels out, and I get V is equal to the square root of 20 times h. Right, multiply both both sides by that. 2 to get rid of the 1/2, and then take the square root. Now, if you're thinking to yourself, I already knew how to do this problem, Mr. McGrath, because we learned how to do this in Unit 3 when we had kinematics equations. I could have just done this. In the vertical direction, the acceleration is -10. The VI is 0. The VF is what I'm trying to find here. And the delta Y would be the height that it's dropped from, but it's going down, so the change in height would actually be -h, right? And then kinematics equations, I would dig up this one, and then I'd plug in the stuff that I have, trying to find VF. The VI is 0, so that's gone. And then 2 times acceleration times delta Y. And then, sure enough, we get the same answer. So we can do it this way, but we can also get it now using energy considerations. And that's kind of cool. Now there's other situations where that this opens up for us where we didn't know before what to do. So let's say we have a spring, that's what that squiggle is, and we've got a little cart that's compressed up against the spring, and the spring has a spring constant of K, and it's compressed some distance x. The spring is, the cart's pushed up against the spring, and we're gonna release the cart from rest, so it's velocity 0, and then after we let it go, it's gonna be zipping along here. So what would that look like? So in the beginning, in my situation A here, the cart is, ooh, that's a funny looking bar, sorry. The cart's compressed up against the spring. Now it does not have any velocity, so there's no E, oops, sorry, that's EE, not EK. Just fix that. That's EE. So there's energy stored in the spring there. And then when we let it go, oh, what should we put here? We're going to put the cart and the spring. And you can put the entire Earth in there. It's always a good idea to do that. But this doesn't change height, so I don't have to worry about EG because there's no change in height. So like the EG would be the same on both sides. It would be 0 because we'll just say that that's the 0 height. And then at situation B, it's all EK now. So what does our equation look like? Well, it's just EE, and it's turned it into EK. And now we can actually put equations to this. So 1/2 kx squared, that's what EE is equal to 1/2 mv squared. And if I wanted to solve for, the problems you're going to do, you're going to have numbers for these things. But if I wanted to solve for V, for example, the 1/2 would cancel out. I would divide the m over to the other side, and I would get the square root of k over m times x squared. So you can solve for that velocity. So there's a lot of great stuff, a lot of cool things that we can do with these energy models and solve for things that we could not have solved for before. And that's where we're headed with this.